Dear participants, welcome back to the fourth day of 5-day FDP series. Today's session, it will be a different altogether. So it is based on interdisciplinary subject. That means, medical with image processing. So this session will be going to be delivered by Dr. B.S. Mahanand, Associate Professor, Department of Information Science and Engineering, SJCE, Mysuru. He was a Raman postdoctoral research fellow at Harvard Medical School, Harvard University, USA. He received the bachelor's degree in computer science and engineering from AIT Chikmagalur, master degree in computer science and engineering SJC Mysore, and PhD in computer science and engineering from VTU Belgaum. Dr. B.S. Mahananda has received Best PhD Thesis Award for the year 2012-13 from Government of Karnataka's Board for IT Education Standards. He was a visiting researcher at the Laboratory of Biomedical Engineering, Helsinki, University of Technology, Finland in year 2007-8. He was a postdoctoral research associate in the Center for Computational Intelligence, School of Computer Science, Nanyang Technological University, Singapore in 2012. He was also a visiting scientist at the National Magnetic Resonance Research Center, Bilkent University, Turkey in 2015. Dr. Mahananda has published more than 40 research articles in various peer-reviewed journals and reputed conferences. He has contributed as a program committee member, special session chair in a number of international conferences. His research interests are in the areas of computational neuroanatomy, medical image analysis, and machine learning. So we are very delighted to have him on board. So once again, I heartily welcome him to this session, and also I welcome all the participants. Right. So this is the fourth day. It will be a very different experience for all of you. So stay tuned till the end. And now it's over to Dr. B.S. Mahanand for continuation. Thank you, Mahanand. Mahanand,
Okay.
yeah, you can.
First of all, good morning, everybody. I would like to thank, Dr. Parmesh for having invited me for this, FDP program. And also, today's topic will be on, as Professor Parmesh mentioned, I'll be speaking on, artificial intelligence and its application in medicine. So we have been hearing a lot about artificial intelligence, which has taken a very big step in the recent years. So a lot of challenging problems are getting solved using AI tools and AI approaches. Since this FDP is on some of the current trends and also the future challenging avenues, which has to be there in computer science domain, I thought that make this talk more of an interdisciplinary or a multidisciplinary approach, wherein how AI tools or technologies can be used for medical problems. So I have been working in this area for quite a long time. So that's why I thought that it's not only AI can be solved for general computer science applications, or it can be solved for mechanical or civil applications. AI can also be used for medicine and health related solutions. So I'll be speaking on basic introduction to artificial intelligence in the initial say slides, and some of the histories. I do know that the previous speakers have spoken about some of the basics of AI. Later, I will concentrate more on the applications, and also the some of the recent uh, methods or algorithms which is developed to solve the medical problems. So just a brief history of AI. I do know that many of you may be aware of this, but just to bring the background, uh, uh, I think just is the term AI a new? Generally, the term AI or artificial intelligence is not a new term. Only thing is, like, nowadays we have been hearing a lot about AI, but if you search the history, the term artificial intelligence has been coined way back in 1950s. So what I'm telling is, it is the term artificial intelligence is there from long time. So I'm telling you, it's over 60 years. So the term artificial intelligence was coined way back in mid 50s, in 1956. So they wanted to mimic the intelligence part of it. Okay. So just for the audience, I just wanted to say that the term artificial intelligence is not new. It is pretty old. Only thing is, we are seeing a lot of its application in recent times. That's why I just wanted to bring this point that term artificial intelligence is not a new term. So just to go back to the history, you may be aware of it. The reason why artificial intelligence came into existence is because the computer scientists wanted to mimic the human intelligence. When I say human intelligence, the intelligence is primarily defined by a couple of factors: the way we perceive, the way we think, okay, the way we act. So if a computer, or if I can mimic this intelligence what the humans have artificially, then it becomes an artificial intelligence. So the work started way back in 1943. It's a very famous McLeod and Pitts model, wherein they tried to simulate the neurons which is present in our brain, and they called as artificial neurons. Then came the first neural network computer, okay, way back in 1956, okay, wherein Minsky and Edmonds, built a first neural network to do some simple, operations, okay. Then what happened is, the boom happened. So way back in from 1956 to 1969, lot of work on neural networks started. They started to implement small programs, small applications, additions, then some of the logical operations. So a lot of small applications of neural networks. All these things started. Then because of the importance of this neural network, okay, then the birth of expert systems came. Okay. So what is an expert system? A system which can make correct decisions. So there was a boom for around 10 years from 1969 to 1979 on expert systems. Then came the application of these neural networks, expert systems, in general, artificial intelligence in the industry also. So what I'm telling is, the application of AI is not new to the current generation. It's been there from long time, over 30-40 years, and it's been applied for a lot of real life and industrial applications. Then what was the problem? Okay, why we didn't hear about artificial intelligence probably 15 or 20 years back. Why there is a sudden interest on artificial intelligence, machine learning, deep learning, all these words or all these approaches? The reason why the artificial intelligence was the research or the application of artificial intelligence came to stand still is because for this reason. So we normally call this as an artificial intelligence winter time. Okay, that is called AI winter. Why AI winter? After 1990s, because most of the AI problems were very complex. Okay, and also during 1990s, we didn't had this huge computing powers. So, for example, nowadays most of the artificial intelligence or deep learning models are built on not on the CPUs. Okay, central processing unit is it is built on GPUs, graphical processor units, isn't it? So, because of the advent or because of GPUs which came into existence, lot of these complex problems which have millions of images can be searched within minutes, and I can do a face recognition of millions of videos, okay, in a matter of minutes. This all, and I can apply deep learning, machine learning, and AI approaches. This is primarily because of the advent or because of the technology on the computing resources. So because from 1990s complex problems were never used to solve the using the computational means what we had at that time, probably the Pentiums 1, 2, 3 and all these things. So the application of AI was not used very much in most of the industrial and real life applications. Then came what? Then thanks to the a huge RAM capacity what we have now, thanks to the cloud computing, thanks to the GPUs, okay, I can process any number of complex problems in a within a fraction of minutes or seconds sometimes, depending on the data. And the data what I'm handling is also very huge. So then the AI basically got a rebirth. So what I see is then the AI basically probably from 2000 onwards, okay, 2005, 2010 onwards, a lot of people started thinking or talking about AI, and AI has been used widely in many applications. Okay, so I just wanted to give a quick background about AI, because I know most of you may be knowing this, but the idea was to just say that artificial intelligence was there from couple of for 5 decades, so it's not new. Why there is a sudden interest? Only because we do have a computational power to solve any complex problems. That's why AI has taken a rebirth in last 1 decade, especially in last 5 years. Then it's been widely applied and also used in a lot of applications. As I said, I would not like to uh, focus more on how AI can be applied in natural language processing. Many of you have been knowing, Google Translator, Siri, all these things. Natural language processing is one of the important topic. Then we do have, AI can be applied in, various other domains. We have been seeing a lot of applications in civil engineering. Of course, the primary application of AI was in robotics. Okay, because one of the fundamental application which started, which is very primarily used for AI was, robots. So robotic arm for surgery, or a lot of robotic applications. So AI and robotics have a very good kind of a mutually exclusive thing, wherein both both go hand in hand because robotics played a major role in AI growth. Then what happened? Then people started using why AI is only limited to robotics or any other applications. AI can be used in medicine also. I'll give a simple pictorial representation. What is this AI in medicine about? Probably, if you see this picture, this will tell the story. Okay, those who are not very familiar with the application of AI in medicine, I'll give a quick kind of a differentiation. If you see the current general medicine or healthcare system, it's primarily based on evidence. Okay, what do you mean by evidence? For example, a person has some fever. Okay, the first thing the doctor says is he tells that get a blood test uh, uh, checked. So when you say a blood test checked, so in the blood test, primarily, all the parameters related to blood, which can be glucose level, it can be related to the HbS, or it can be related to creatinine. So you take a blood report to a doctor. So the blood report acts as an evidence for the doctor. So based on the report, it's not necessarily blood report, any report, okay, or it can be any of the the reports what you say, it can be X-ray or whatever it is. So he has some sort of a lab report. Based on the lab report, what happens is, once I have the lab report, so he sees the parameter, normal parameters, and also the other parameters. Once the parameters are checked, if it's on a higher note or if it's on a based on the threshold, the doctor basically makes a decision and gives you a tablet. So fundamentally, the medicine is prescribed based on the evidence and also the symptoms. Okay, I think most of you will agree on this, on evidence-based medicine, which is primarily on symptoms and also based on the lab reports or the some of the problems what the person has. So then a doctor will prescribe it. What we are talking is, there is a lot of scope which is beneath the surface. See, if you happen to see here, this is only tip of an iceberg, which is primarily used, which is evidence-based medicine. Which is hidden? If you see here, there's a lot of stuff which is hidden here or which is beneath the surface. We call this as an intelligence-based medicine. Okay, what is intelligence-based medicine? So I use computers. Artificial intelligence can be used to basically make a better diagnostic or better decision for some of the diseases. So if you, this primarily figure probably acts as a basic motivation for why AI should be used in medicine. Okay, so I just wanted to bring this point. So from evidence-based medicine, we are moving towards intelligence-based medicine. So I'll explain how this can be done in my future say slides. Basically, what is intelligence-based medicine? So I'm using AI techniques to detect, for early detection or to check the progress of the disease. That's all. Okay. So those who would like to do some research on AI application in medicine, what I'm telling is, there is a huge opportunity. Okay, opportunity to explore all these AI techniques in a huge field, or which is an important field called in the field of medicine. Okay, so just to quote the famous Hungarian doctor, so what he said is, in future, the artificial intelligence will be the new stethoscope of the 21st century. So I'm not telling that we'll be replacing the general stethoscope used by the doctors. Of course, that will be there. End of the day, the decision is made by doctor only. So he makes a decision. But what AI can bring in is, I do know that a lot of times doctors are humans. They do make mistakes. So there is some medical error which can happen. So the fundamental philosophy of this AI in medicine is to minimize the medical doctor's error, which normally happens because of oversight and other things. And this computer-based approaches can help the doctors to reduce the medical errors which happens in a normal routine, or not necessarily to reduce the medical errors. Also, the AI based or intelligence based approaches can also help the doctors to make a better decision. So, and also probably the decision or the solution given by the AI based system can be taken as a second opinion for a doctor. Okay, but I'm just saying we cannot replace the doctor. Doctors are will be there, and because they are the primary persons who basically treat us. But AI can basically act as probably an aid to a doctor, so that they can make a better decision, and also some of the medical errors which normally happens can be minimized with the help of AI based systems. See, that's the motivation I wanted to bring in. So that on that context, it was said that AI based tools in medicine will be the new stethoscope of 21st century. So that's the background I have. So as I will just reiterate, there is a lot of opportunity which is hidden beneath the surface. It's my some sort of a suggestion wherein those who want to start some sort of a research journey, there is a lot of opportunities wherein you can apply AI techniques to medical problems. Okay, I will give one case study on how AI can be applied in dementia, which I've been working for past 10 years. So I'll give that case study, or some of the research which has happened in that area. But it's not only restricted to only dementia, which is a neurological disorder related to memory problems in elderly people. It can be applied to other diseases also. So the next slide, just to give some examples, just to create some interest, or how actually this AI has been used. Of course, a lot, as last couple of years or last 5 years, AI has taken a exponential growth, and Google is also working on a lot of AI projects, and recently they came up with an solution wherein they tested a lot of retinal images, and the interesting point is they can detect the cardiovascular the heart related problems from retinal scan. Okay, so this we were never thought of. See, normally if there is a heart problem, we used to go to a doctor, a heart specialist, and check our the blood pressure, and how actually my heart is functioning. But it's very astonishing that I can detect heart related problems using my eye scan, or retinal scan. So that's the power of AI in medicine. So since we are focusing on medicine, I am taking this example. Okay, it's actually published in AI journal. So the reason why I took this example is because it has a tremendous potential to do a lot of research, and also a lot of applications have been not yet done, which we never thought of in the previous few years. That's why I took this example, which primarily says that you do a retinal scan. I can primarily say whether there is a heart related problem or cardiovascular related problem in the heart. Okay, so this is already published. Those who are really interested, please you can just get more information in the paper. Okay, so some of the other applications which is done by another similar applications which is on a precision cardiovascular disease. If you happen to see here, there is a huge data available, because now data is not a problem. So we do have data. If you are wearing a Fitbit, the Fitbit server has all your data, till you breathe. So that's the huge data what it has. It has all the the pulses, all the parameters. So it's not only Fitbit. There are many data which is available, which can be basically used. For example, if you take a big data, there is a lifestyle data is there, genetic data is there, gut microbiome, diet plans, social media has also a lot of data, omnic data is there, wearable technology. This was I was telling, the Fitbit and all these things which you are trying to use. And we do have a cloud-based system which can be stored. You don't have to store it in your physical server. There is a cloud-based approach. Then we do have researchers and physicians, okay, which can be used anywhere, anytime in a cloud platform. So then comes the the primary thing, which is artificial intelligence. As I said, artificial intelligence is primarily the main focus, or primary driving factors are cognitive computing, machine learning, and deep learning. So these three approaches basically drives the artificial intelligence as a whole. And what do I do with these technologies? Either I can go for a supervised learning, or I can go for an unsupervised learning, or I can go for a reinforcement learning. So these are primarily different three ways of learning in any of the artificial intelligence approaches. Supervised learning means I know the output. Okay, many of you may be knowing this. If you want to just get a feel of this, the output is known. For example, if I am classifying two objects, okay, so I train and test. So what do I do with that? So the testing samples, the category is known. So in unsupervised, I don't know the outcome. Output is not known. I don't know which category they belong. That is unsupervised. Similarly, reinforcement learning. So generally, when I have an artificial intelligence system, I can choose any of these learning methods. Sometimes I'll be knowing the outcome. Sometimes I'll not be knowing the outcome. Sometimes I may have to reinforce the learning. Okay, I need to do a predictive model. Okay, so this diagram primarily illustrates the overall framework of how AI applications can be used, or AI can be used using a big data, using cloud computing, and also the physicians or the researchers who are there part of this system ecosystem. What we have AI in medicine, or this was taken for cardiovascular medicine, can be summarized. And also, just to give an illustration, researchers at Oxford University have developed a diagnostic system in which what they do is the AI system has diagnosed the heart disease compared to normal, the physicians. 80% of the time, it was correct. Okay, so 80% is a very good kind of a accuracy in medicine. Okay, of course, it cannot be 100% even by doctors. So 80% of the time, if the AI model is accurately detecting, then probably we are in the right direction. Okay, so that study was validated with the actual physicians and also with the AI's output, and it was a very promising result that motivated most of the researchers to take up AI based approaches for medicine problems. Okay, so I just wanted to give this picture so that how the different technologies, for example, the huge data what we have, cloud-based sharing, and the AI can help to make a better decision. This model not necessarily can be used for cardiovascular medicine. This can be used for diabetics also. The same framework can be used for diabetes, or the same framework can be used for other diseases also, but the fundamental framework is the same. Okay, so if I have a data, I can always apply the AI based approaches and then make a better decision. Of course, I will have my the final decision making is done by the professional doctor, but this can help him to make a better decision. That's the fundamental point I was just trying to emphasize. Since this point has been made, okay, let's move on to one of the interesting topic which I have been working for for more than around 10 years. So I'll explain how AI in dementia can be used. Okay, so those of you who are not familiar with what is dementia, so dementia is a memory related disorder wherein people, when they tend to grow old, they tend to lose the memory problem. Okay, normally it is said that when you are getting old, you are basically you lose memory, but there is a disease called dementia. Specifically, it's called Alzheimer disease, wherein just because you are getting old doesn't mean that you should forget. Okay, so if you happen to have, if you are forgetting primarily quite often, so it is not a normal aging problem. It can be a disease called dementia. Okay, so I'll just give this case study of how AI can be used in dementia, and also you can primarily explore similar AI tools can be used for other diseases. For example, diabetes, cardiovascular diseases, or it can be for autism. It can be for Parkinson disease. Any disease you can name. But I am just focusing on how AI was has been applied in dementia, because I can show some of my the results, so that you can get the overall feel of it, and then you can apply similar models for your own research problems. Okay, so as I said, dementia is one of the most common diseases in elderly. Why I say elderly means when the people grow old, they have this problem of forgetting. So we should not mistake the problem of forgetting as a normal aging process. There can be a disease called Alzheimer or dementia in general, and the problem with that is, if you happen to get this disease in so the lifespan is very short. So within 6 to 8 years, people, there is a high chances of dying. Okay, So what causes this dementia? Okay. The causes for dementia is primary cause is Alzheimer disease. Most of you may be heard of it, or vascular dementia, Lewy body disease, frontotemporal dementia, or there are other less causes. Okay. So, but the primary cause for this dementia in general is Alzheimer disease. So Alzheimer disease has been like 70% of the cases of dementia causes is caused because of Alzheimer disease. Let's talk about this Alzheimer disease. Then I will move on to how this AD problem can be solved using machine learning and other image analysis problems can be applied. So what is this Alzheimer disease? Alzheimer disease is a progressive degenerative disease that leads to memory loss. Okay, as I said, primarily you lose your the person will lose the memory loss, judgment, he can't make a judgment, and problem in learning. Okay, that's the one of the basic characteristics of a Alzheimer disease patient. So is it new? No. This was first discovered around 114 years back. Okay, long time back. 1906, the German psychiatrist called Alois Alzheimer discovered this problem in a person. Okay, so it's been there from long time. And also the main problem with this disease is still this disease is not properly understood. When I say properly understood, in the sense we don't know the exact cause. Since I don't know the cause, I don't know it becomes very difficult to cure also. Okay, so if you don't know the cause of a disease, it becomes very difficult to find a medicine also. Okay, and also because it is so prevalent, in September month of every year, it is actually considered as a Alzheimer's month, because this is a very alarming or one of the disease which is very threatening to the public life. So that's why the World Health Organization has announced a day for Alzheimer, which is called 21st September, is also celebrated as Alzheimer Day. Okay. See, why I'm bringing these points is so that this is an important disease and a lot of work can be done in this area. Okay. So you have to choose a problem wherein which has been less explored. Okay. So the reason why this problem can be taken, or which is very important, is at present researchers do not know a single cause nor a cure. So it is still a good research area to work on, so that using some AI-based applications, you can at least try to detect the disease early, so that the disease can be prolonged. Some sort of an intervention can be done using some of the AI tools. That's the reason why some of these AI tools are helpful in some of these life-threatening diseases like Alzheimer. So just to give the numbers, actually there are 40 million people in the world with this disease. Okay. Only thing is we may not be aware of the statistics. 40 million people is a very big number. Okay, and since people are getting old, it is basically going to quadruple 4 times in another 50 years. So it's a very serious problem. And what the statistics says that by 2048 or 2050, at least one person among 45 people will be living with AD, which is very disturbing. And also, if you happen to take our own India's case, the statistics there, it shows that there are more than 3.7 million Indians which are affected by dementia, and most of the dementia cases are around 70% of are Alzheimer's. Okay, so that's the prevalence this disease has. So, And also a lot of Americans, a lot of Europeans, many people are affected by this. Just to give a statistics, there are around 5.3 million Americans affected by AIDS. Okay, so that's the background I have. Then how do we diagnose this? This is the typical solution part. So I had given a brief introduction about of AI, why AI is important. Then just a you know uh, overall understanding about why dementia, what is dementia, and what are the causes for dementia, and primarily the Alzheimer disease, how what is why it's so important problem to be solved. Okay, how does a doctor diagnose a disease, for example, generally? So there are set of standards. Okay, so I do said it is primarily evidence based. Most of the doctors do evidence based medicine, but we are moving towards intelligence based medicine. So there are certain criterias. So this is called as it's there in the screen. It says Diagnostic Statistic Manual (DSM). It's been revised quite often, periodically. So they have listed symptoms for most of the mental disorders. Okay, for depression, they have listed symptoms. For dementia, they have listed symptoms. That if there is one test called MMSE, Mini Mental State Examination, wherein it is a 30 question 30 question test. So out of those 30 questions, if you have if a person happens to score less than 24, then based on the test, then doctors will primarily have a suspicion saying that that person may have a Alzheimer disease. So when I say 30 questions, those 30 questions are very simple questions. For example, what is your name? Okay, where do you live? What is your home address? So these 30 questions are very basic questions. Okay, so that even if a person can't answer the basic questions, then the doctors primarily make a diagnosis saying that he may be having some sort of a memory related problems. Okay, but what is the problem with this? So I'm not saying that the clinical diagnosis criteria uh, is a good choice, is the first thing what every doctor will do it, or people will use it. But traditionally it involves a lot of interviews, right? Time consuming interviews. The person has to go to a doctor, and he has all the symptoms, everything. Interviews primarily, time consuming interviews are there. And also if I get a score some value in my test, that score is primarily dependent on the various factors: age factor, my intellect, IQ factors, language ability, all these things. I may not be able to express properly, all these things. And also sometimes it can be error prone. Why I say error prone is, generally if a patient or a person can't answer this, then his family member or a caregiver will answer. Normally there can be a bias when a caregiver answers or a family member answers on behalf of a patient. So because the person who is undergoing this problem knows it better. Of course, since he is not in a position to explain, the other person, the family member or the caregiver, cannot be very 100% sure what is happening in his body or mind. So that's why it's called as error prone. Sometimes it can be error prone, and sometimes what happens is the process of interview, and also going to a hospital, meeting a psychiatrist, this can be maybe uncomfortable. All these factors are there. Alternatively, what we can use, we can go for a image based approaches. Traditional tests are also important, but the research avenues are moving from a traditional approaches to a imaging approaches. What are imaging approaches? The imaging approaches, the moment we hear a word called imaging, we hear about X-ray, isn't it? It's been there from long, some time. X-rays are there, and what's the problem with X-ray? X-ray, it's a very convenient, affordable imaging modality, but the only problem with that is the resolution is not that great. Okay, then what happened? CT scan. Then computer tomography came into picture, so the resolution is more compared to X-ray. Then also detailed informations can be got in the CT scan, and also CT scans are reasonably priced. Okay, so and I can get a better view or better diagnosis can be made uh, as compared to X-ray images. So CT has been used widely, and also it's been there. Okay, what are the problem with CT? Is the CT image is the final image or a modality I can use? No, even CT images lacks some spatial resolution. Okay, when I say lacks spatial lower spatial resolution compared to other imaging modalities which are there in the which are normally practiced in other radiology modalities, CT scan has a comparatively low spatial resolution. And also the other thing is, if I want to detect a disease early, then because of the lower resolutions, sometimes it may so happen that the early detection of the disease may be difficult to do it. Okay, that's the point I'm trying to do. Then what is the alternative? Alternative can be MRI. Okay, so sometimes if you need a high spatial resolution, you want to detect the disease in early stages, then MRI is widely used. Why we use it? Because of a high spatial resolution. It has exceptional soft tissue contrast. The important point is it can detect minute abnormalities, and more importantly, we can visualize and measure atrophy rates. Okay, change, growth in the brain. So that can be easily visualized. There are a lot of MRI based techniques. There is a technique called regular MRI is there, MRI which is primarily used. There is fMRI, functional MRI is also there, which gives me the neural activities. There is DTI also, which is an advanced MRI technique called diffusion tensor imaging. There can be MRS also, magnetic resonance spectroscopy. So all these imaging MRI techniques can be used for different applications. Okay, so that's the brief introduction about the MRI, and MRI are have a greater advantage compared to the other imaging modalities. So when it comes to brain, how do I detect the changes in the brain? The changes in the brain can be done using two approaches, widely used approaches. Those who are doing research on any of the medical imaging problems, or even general imaging applications, one is a region-based approach. The other one is a whole brain approach, isn't it? So typically we'll have two types of approaches: ROI approach, or I don't want to look into the only ROI, the region what I'm looking. I would like to look into the whole brain also. I can see the whole brain and I would like to analyze the whole brain. Why only one region? But fundamental, two different categories in analyzing any imaging applications is ROI based, another is whole image based. Okay, so just to give an a quick view on what is this ROI based approach, many of you may be knowing this. So if you happen to take an MRI, what we can do is just take let's say if it's an Alzheimer disease patient, I know that the hippocampus region, it's there in the medical literature saying that the hippocampal region or thalamus or some regions, specific region of interest, have some problem. Okay, sometimes this may become very small, so that there is a problem, or sometimes in case of a brain tumor, if you say the tumor is growing big, so I can identify the region in which the brain tumor is there. So that is a ROI approach, wherein I can exactly go to a region and do an analysis on it. So what is the analysis I will be knowing? The volumetric measurement of a specific regions can be done. Okay, and also I can go to that particular region and check the tissue loss or the abnormalities which is present in that region. So this has been followed from quite a long time, ROI analysis. But what is the problem with ROI analysis? So ROI analysis normally have some shortcomings. So this has to be manually traced. When I say manually traced, the doctor has to say there is some problem, or a radiologist has to say that there is a problem here, manually traced. Okay, and sometimes because of the complex nature of the brain, and brain has a lot of overlapping sub areas or regions, it is depending on the person who basically does this boundary. Okay, tracers or the radiologist's experience. Sometimes he may draw a bigger region, and that region may not be hippocampus, it can be something else. And also it can be time consuming. Since there is a manual intervention involved, it can be error prone also. Okay, error prone. So ROI analysis is a good approach. I'm not denying it. It's been widely used in many applications. It's also used in Alzheimer's disease also. I'll share the literature on it. But only thing is, provided if you know the region, if the it's been properly identified, the boundary of the region, then it can be useful inference. Okay. Sometimes during the early stages of a disease, the ROI cannot be located because it has not been progressed so well so that the scan can detect it. Okay, it may be there, but the human eye may not be able to detect the initial growth of a tumor, or in generally growth in particular age. So even though ROI has been widely used, a lot of people use this. So I just taken this example. How does hippocampal change? Atrophy means changes. How hippocampus region gets changed in a normal person, also in a elderly person. So there was a study done by Paul Thompson at University of California, Los Angeles, wherein they took elderly people, like people more than 60 years. They took normal persons also. Okay, uh, uh, normal persons, and also they took the Alzheimer persons. So then they compared in one particular region called hippocampus, they compared the growth. So they followed this for 2 years. They followed this for 2 years, and they wanted to know the difference, what is happening in this particular area. Is that the growth has increased or growth has come down? So that's one of the analysis what you can do in ROI, wherein go to a particular ROI and you can notice the change over a period of time. Okay, or you can notice a change during that time point. Okay, you can either do a longitudinal analysis, that how this brain region is changing for 6 months, 1 year, or 2 years, or you can also make a analysis how it looks like now. Okay, two ways of analysis. So even though this is widely used, what we are talking now is, which is widely used, is called as a voxel-based morphometry. Okay, so I would like to emphasize more on this voxel-based morphometry. Most of you may be aware, or some of you are not aware. This is a very good approach. This is not an ROI approach. This is primarily a whole brain analysis. Sometimes what happens in some of the diseases is it becomes very difficult to identify which region the problem lies. So what happens during those times? So it's always a good practice to look the whole brain rather than looking the minute parts or regions. So what does this voxel-based morphometry does this? It is an image analysis technique which identifies the gray matter or a white matter which is present in our brain, the differences between them. What is the difference of gray matter between a normal person and a diseased person? Is the gray matter is increasing? Is the gray matter is decreasing? Okay. So just to give a background, in a brain, there are three. Brain is made up of three matters. One is called as a gray matter. Another one is made as a white matter. The third matter, what is present in our brain is human brain is CSF. CSF is the cerebral spinal fluid. Cerebral spinal fluid. These three matters are present, but for the general research purpose with respect to Alzheimer's disease, we normally look into the white matter or the gray matter. Is primarily used for the studies. Why do we use this voxel-based morphometry? The voxel-based morphometry is a fast automatic method. No manual intervention is required, so it does automatically. And there are three basic steps in it. The three basic steps are: first I segment, then what do I do is I smooth the image, and finally I do a statistical analysis. Okay, I'll pictorially explain this so that you will understand this better. Take any image. Okay, it's a very whole brain approach. No need to know the a priori knowledge. And there is a software called SPM. You can Google it. Statistical parametric mapping. SPM is the tool name. Just give the input MRI. It does automatically the segmentation. When I say segmentation, it segments gray matter, white matter, and also CSF. So it segments into three regions, and we are interested in gray matter. I take the gray matter. Then what do? I use a Gaussian kernel, smooth this, and finally we do the statistical analysis. Okay. So this is a very simple process which is widely used by many researchers. For any given image modality, I can do this three simple steps, and these three simple steps are automatic. Okay. So these tools are available in a tool called Statistical Parametric Mapping, SPM. You can just Google SPM and VBM. So you get the software, free open source software, and you can start working on it if you have a problem related to image analysis and medical related things. So just a representation. This is the original MRI. I segmented. I am interested in gray matter. Of course, if you want to do a white matter study, you can get the white matter segmented image also. Then I smoothen it using a Gaussian kernel. Okay, just to average the regions or the voxels around it. Then what do? We primarily do a statistical analysis. So when I do a statistical analysis, what we do is the statistical analysis says that if I have a group of patients, let's say 50 people, and group of normal persons. So what is the difference between these two groups, normal versus patients? So the final output of this VBM analysis is the regions which is depicted in in red are the regions where there is a problem. Okay, this is what I am trying to show. This is automatically got. No a priori information. No a priori information is got. The computer, the algorithm primarily gives you this region, stating that there is a problem in these regions, so that the difference can be easily located. This is what the final outcome of a VBM analysis is. Of course, I can render this. I can make a three-dimensional approach just to get a better view of it. So it's a 3D, view is also can be got. Once I have these things, this is the image analysis part. Where is the machine learning or a AI part in this? Okay. So this is where the AI comes into picture. Okay. Just to give a background on AI and the Alzheimer disease. This is a very important paper which is cited very well by most of the people who are doing research on Alzheimer disease. So very good paper in a reputed journal called Neuroimage. What they did is they did a automatic classification of patients with Alzheimer disease using MRI, and they compared 10 different methods. So this will be a good starting paper for you to start the research. Always go for a paper which compares other methods. So once I have this paper, very good paper, the findings from this paper is they compared, on one single data set, they compared all the methods. So just to give a summary of this, the idea of this they compared is they took the gray matters. One person took gray matter. One researcher. The others have taken gray matter, white matter, and also CSF is another approach which they have taken. Some people have used support vector machine, which is widely used. Some people, and most of them, have used SVM in this approach. Some people have used logistic regression, and some have used random forest approaches. The usual machine learning approaches which is being used have been applied. And the interesting point in this is they would like to understand how this machine learning classifier is able to detect the disease called Alzheimer disease using different feature extraction techniques. That's the primary objective of this. And the study found that most of the studies are primarily based on Voxel-based analysis. As you see here, it's a Voxel segmented tissue probabilities, and also a promising result has been got using the Voxel approach, especially the whole brain approach, which is primarily used. And the people have touched around 92% of the accuracy has been already published, so that it can be further improved. So I will touch upon some of the latest work which has been published in the recent years, which is primarily based on a new classifier called as Metacognitive Neural Network, which is called as MCNN. Okay. Of course, the widely used approach is called as a support vector machine. Since this workshop is primarily based on some of the newer challenges and newer approaches, I will introduce a new or a recent approach which is called as a metacognitive neural network, which has been used in most of the application, and also I will share some of its results so that you can apply the newer algorithms in your respective research domain. So as you know, for any machine learning algorithm, feature extraction is one of the important criteria. So I can extract the features. Where do I get my features? Features can be got from my MRI. So the flow diagram which shows that I take the MRI, I do this voxel-based morphometry, I get some regions. The regions are the red regions which we got in the previous slide can be used as a features to train my classifier. Okay. So what are the features for my algorithm? The features can be these red spots. Here it is represented as black and white, but we can take that as a major clusters which are regions automatically detected by VBM, and feed as a feature vector to my classifier. This is a simple scenario for a feature extraction process. Once I have my feature extracted and I have stored as a feature vector, the next thing is to apply any classifier. You can apply support vector machine. You can apply, other random forest. You can apply naive-based classifier. You can apply, decision trees. Okay, or you can apply deep learning models. Any things can be applied. But here I am introducing a recently proposed, new classifier, which is called as a metacognitive neural network. In short form, we call this as MCNN. What is this MCNN? The MCNN is a recently developed, algorithm which is primarily based on human metacognition. Okay, what is human metacognition? The simple analogy is, normally the traditional classifiers will take all the samples. Let's say if there are 100 apples, if I want to train, okay, or if I want to classify, I use all the 100 samples for training. But in metacognitive neural network, the difference between traditional classifier and metacognitive neural network is, the metacognitive neural network works on the principle of human cognition. What is human cognition? As soon as a new sample comes, if I already know about it, what do? If I know the subject, for example, normally happens, if I know the topic, I am very curious to learn. So I will input it into my model. If I already know this, I don't have to train it. I can delete it. Okay. Sometimes what happens is, I am in a dilemma whether to keep this object or whether to keep this sample or whether to delete it. During those times, I can keep that in a reserve. So this philosophy of deleting the samples, learning the samples, and also reserving is a new concept which is used in a metacognitive neural network. So if you happen to have a same sample with the same information, do not use it because I already know about it. If there is a new information which comes, then please learn it. If it's already known, you don't have to train it. You can always discard it. If you are in a dilemma whether to use it or not, that you can keep it in a reserve, okay, or a backend. In other words, the philosophy of sample learning, sample deletion, and sample reserve is a new concept in the neural network area. It's a new concept in the AI field, wherein it has a lot of potential applications. Just to give a pictorial representation of this, I can show. This is a traditional classifier. Every training sample comes. There is a input layer, a hidden layer, and a output layer. Okay, any machine learning algorithms will have this architecture. What is metacognitive neural network? The metacognitive neural component is, so I build a cognition about a cognition, metacognition. This is cognitive component. This is metacognitive component. In the metacognitive component, what happens is, so I build a layer above this, or I build a measures above this, so that based on specific criteria, I can always say that whether the training sample which comes should be deleted or should be used or should be reserved. So I make this decision. Then I feed it to my network. If it's a old information which is coming again and again, I can delete it. Why I should train the same information? If it's a new information, I will add it to my network. Sometimes I am in a dilemma whether to use it or whether to discard it. So if you are in a dilemma, you can keep it as a reserve. You can use it later whenever you want it. So this philosophy of deleting, updating, and reserving is primarily done by humans. So we all do it. If I already know, I don't give much of an importance. If I don't know, I am very curious to know. Okay. Sometimes there is a topic which we learned during our engineering days. So it will be in the reserve. Then that reserve will trigger, in the current context. So this philosophy of metacognition is very widely used, and I suggest a lot of young researchers who are listening, so that along with the traditional classifier, metacognitive neural network can also be used. And it is very recent. It's not very old also. So any applications on metacognitive neural network for any of the classification problem, clustering, the predictive problems can be used. So just to give a simple example, I am taking one example. I am coming to the last part of my talk, which is on results. So it's not that it's only the theoretical stuff. This has been used on a actual MRI data. So there is a open source MRI data available for Alzheimer's disease. Not necessarily Alzheimer's disease. Many diseases have a open source data. You can download, you can Google it, you can browse and download them. Then what you can do is, so in this case study or the work which I am presenting, it was downloaded from open repository called OASIS, Open Access Series of Imaging Studies. We took 100 normal persons, 100 AD patients, and 98 normal persons, just to have the sample balance. Okay, so 100 and 98 normal persons. And these are all MRI images, 3-dimensional MRI images, which are taken from 1.5 Tesla Siemens scanners. Okay, so this is a general brief introduction about the data set. Then what we did is, we did the same thing. Okay, we did a neurological significance study. How I can do that? I know that Alzheimer's disease is a age-related problem. Okay, so I can compare normal person and AD patients. That is complete data. That is one thing, irrespective of the age. So I group everybody in one as patients and everybody as normal persons. So I can do a statistical analysis, I can do a classification on it, and primarily I can get an accuracy. Alternatively, since it is a age-related problem, I can also do an additional secondary analysis based on age. What is that age analysis? I want to know what is the brain regions which gets activated for the age group between 60 to 69. That is one study or a sub-study. I want to know how does a brain changes with a person whose age is 70 to 79. Then I wanted to know how does a brain changes or brain activation happens in an age group of 80 and above. So this is a deep analysis what we can do in any of the medical problems. One problem is just take everybody together and do that. And alternatively, you have to go deep into the problem. You can also do a gender analysis. How does the problem with male and female differs? We all know that male and female brains are different. Okay, physiologically there is a difference between male and female. So I can do a gender analysis also. In this study, what I am showing is done using age analysis, age study, and also I took everybody as a complete data. Since when you are dealing with MRI, there is a huge amount of data which is available, and I may have to do some dimensionality reduction or feature selection or feature reduction. So in this study, there is a feature selection used is called recursive feature elimination, RFE. Okay, RFE is the feature elimination technique which is used. Of course, you can use other techniques like PCA, principal component analysis. You can use LDA, linear discriminant analysis. Any technique you can use to reduce the features. Okay, in the case study or in the study, what I am trying to show you, the feature selection was done using RFE approach, recursive feature elimination approach. With this background, I will show some of the results. So just to show this table, couple of tables are left. So I have whole features. The number of features is 19,879 is the whole number of features what we have. Is all the features required? Is the complete features required? No, may not be required. We did a feature selection or feature reduction. When we did the feature selection with the VBM features with RFE, so we could get 906 features. See, from 19,000 we got 900 odd features. Did the same MCNN classifier. See here, the accuracy, there was a tremendous increase, around 8% increase in the accuracy also. What is the reason? There should be some reason for this. The reason is, in the whole features, there are a lot of redundant features which is affecting the classifier performance. I don't want all the redundant features which is present. I need only the prominent features. These prominent features, which are very significant features, can be extracted. It's like a filtered features, which are very strong, robust features, which primarily used for classifications. So when you take a whole features, huge features, there can be redundancy. Sometimes redundancy in features can also affect the classification performance. That's why it's always good to do a whole feature and also reduced features. Okay, so it's a normal thing to do. So you can experiment on different feature size also. Why only 906? Why not 500? Okay, why not 10,000? Or different feature selection, feature reduction sizes can be done, and we can check the accuracy also. In this case, the good accuracy was obtained for 906 features. Okay, that's why the experiment were stopped at 906. This is with the complete data. And also, these are the regions which are responsible for the disease with the complete data. And the red one is the complete data, and the yellow ones which you are seeing is the reduced features. Okay, reduced features what we have. Then the same age analysis. Did the VBM analysis between 60 to 69, 70 to 79, 80 and above. Same thing. Did the feature selection, took the whole features, 25 features. With 25 features, we are hitting 100% with the 60 to 69. Okay. Then 70 to 79, similar study was done. Did the same philosophy. The philosophy is not to increase the accuracy. The point here is, one thing is you should get a good accuracy. You should be able to detect properly. And the other important part is which regions are important, which part of the brain. It's not only these numbers. It also should be which part of the brain are more important is another important factor. So this is the classification performance with respect to different age groups. And also an additional analysis was done with respect to which of the brain regions in 60-year people it is affecting. See, this is a 60-year-old brain wherein it is affecting this region. Whereas 70 to 79-year region, the brain is getting affected in these region. Whereas the people with 80 and above, it is getting affected in this region. So when you do a whole brain analysis, it is not only the accuracy which matters, also we have to explore which regions are the important regions. Of course, we can get these regions always. I can map it back to the main original MRI and find out these regions. For the doctors or for the clinicians, they are more interested in the brain regions. Okay, they want to see which brain region there is a problem. Of course, from the machine learning point of view, we are interested in the accuracy. From the medical point of view, we are interested in the brain regions. So both studies has to be done. You have to identify the brain regions as well as you have to automatically classify also. So that's the final, kind of a message I would like to say. So any applications, it's not only the number what we get, it is also the cause for it, from which region it is coming. that also has to be looked into. Okay, so the concluding slide, it's not necessarily the 100% or the 90% what we get. We need to identify the regions also which are responsible for this. So it was just found that between 60 to 69, superior temporal gyrus is the important region. Between 70 to 79, parahippocampal gyrus is the important region and extranuclear. 80 and above, people have hippocampus, parahippocampal gyrus, and lateral ventricle are the important regions. So different regions are also identified, okay, automatically, and these studies has to be validated. It's not, we can't completely rely on the AI-based approaches. This has to be also validated by expert, psychiatrists, and expert psychiatrists have also validated these regions, because they say that these are the regions which causes Alzheimer's disease. So it has to be properly validated and then reported in the literature. The final concluding thing is to using some of the machine learning as well as image processing approaches, some of the problems related to Alzheimer can easily be identified. The final concluding remarks what we had is between 60 to 69, we had a problem of degradation in the sound processing capacity. 70 to 79, memory related problems. 80 to 89, short-term memory, long-term memory or problem was identified. And in conclusion, I would just like to thank you for giving me an opportunity. If you have any questions, I would like to answer them. Hello. Ready? Mahanand.
Thank you so much, sir. There is no question from participants end.
Off the record, you can also mail me bsmahanand@sjc.ac.in.
Sure, sir.